All right, so the exam is over chapters 6, 8, and 9, and you can bring a cheat sheet as usual, one side of an 8.5 by 11. And I'm going to try and do more like the last review, where I just quickly say what I think are the most important bits of each chapter. So for chapter 6, the most important thing generally is that work is a transfer of energy from one thing to another. And you could have that transfer happen within a system, which is what conservative forces do, or into or out of the system, which is what non conservative forces do. Conservative forces include things like gravity, and we'll look at the spring force later, so mainly just gravity for this chapter. So, what that means is gravity can hand off kinetic energy to a different type, which is potential energy, whereas other forces like friction, they just hand the energy off to something outside of the system, and so you don't tend to get the energy back in that case. Math-wise, for work, what you're going to want to know is how to tell if it's positive, negative, or zero, and that's going to be what this table's telling you. Work is positive if the force acts in the same direction as the displacement of the object. So if you're pushing in the same direction something's moving, that's positive work. If you are pushing in the opposite direction that something is moving, that's negative. If you are pushing perpendicular to the direction it's moving, that is zero work. You can also talk about it in terms of whether it's going to speed something up, slow it down, or not change its speed. Those are equivalent ways to speak about positive, negative, or zero work done. You can expect questions where I give you a certain situation, there's some forces acting on an object, and I want to know, are they positive, negative, or zero? And you just decide based on which way the object's moving and which way those forces are acting in relation to that motion. Explicitly, you may have to do a calculation like this one, but it'll be for multiple forces, and you'll have to find the net work done, and then use the work energy theorem. So something like this question, you find the work done by all forces, and then you set that equal to the change in kinetic energy, and that'll let you find how fast something is going at the end of whatever situation is going on. So the work energy theorem is really your main tool in this chapter, but in the special case where things like friction are not acting, that simplifies down to the conservation of energy. So the other calculation you'd be expected to do is this one, where you say your initial budget of kinetic and potential is the same as your final budget of kinetic and potential energy. Usually that gets written out in full like this. So if you have a problem that looks like conservation of energy, how you would know is it's relating heights of something to speeds. So they tell you it's at height A and then ends up at height B. It starts out with a certain speed. What speed does it end up with? That style of question. Then your first step is what I just circled. Do not skip to a later version of this. For instance, this one right here. Because A, that might not be what you're trying to find for the problem, and B, I might have simplified down based on what's going on in this particular problem. So you always want to start from the most general equation and then see what you can throw out and what algebra you can do. The other conceptual thing in this chapter, besides positive, negative, or zero work, would be knowing when energy is conserved. And that's going to be when external forces are not doing any net work. Mechanical energy only changes if an external non-conservative force does work, or in other words, if non-conservative forces aren't doing work, then mechanical energy is fixed, is conserved. And that's the main stuff for that chapter. Power is not on there. Really, this whole last page is not on there. All right, chapter 8. The main math thing in this chapter is the kinematic equations. So you're given some stuff about angular motion, and you have to find other stuff about that motion. But I'll get back to that in a minute. Conceptually, what I could ask is things like, is this a positive or negative angular displacement, velocity, acceleration, so on and so forth. How you can tell is this sign convention. Counterclockwise is positive, clockwise is negative. And then for angular acceleration, it's going to be the same sign as angular velocity if that object is spinning faster, or you can go the other direction. If you see that angular acceleration has the same sign as angular velocity, then it's going faster. And then if they have opposite signs, the object will spin slower and slower over time and eventually turn back around. Back to kinematic equations, ones like these two questions are guaranteed, basically. I will give you some information about the rotation of something, and you just have to fill in the rest of the details to find the last thing. I'm going to stick to radians, radians per second squared, so on and so forth, so you don't really have to do much conversion, but you will have to do kinematic equations. The other math in this chapter is how to relate angular motion to linear motion. And so that would be, for instance, you're given the angular speed of something, you want to find the linear speed. There was a question over email about how you can tell whether you're dealing with this type of problem versus a kinematics problem. The answer is based on what you're being given and what you're being asked for. So if you're told something about a linear velocity or tangential velocity, or you're asked to find it, you're more in this realm. If you're only being told about angular quantities, then you're looking at kinematics. So what I would recommend, especially for this chapter, is to make a list on your cheat sheet that's something like quantity, variable, and units. And so the quantity might be like angular velocity. The variable is omega. The units are radians per second, or RPM, or several others. And then do the same for every other variable we've looked at. Because then you'll know what you're being given, and if you start labeling stuff like V and A and that kind of thing, and you're given things like omega or alpha, you know it's this type of problem where you're converting from angular to linear or linear to angular motion. Total acceleration won't be on there, but there could be separate questions about centripetal and tangential. In other words, you could have something spinning faster or slower, and that would mean it does have a centripetal and tangential acceleration, but I would ask about those two things separately. I wouldn't ask you to find the total acceleration. For Chapter 9, main concepts would be still the sign convention thing for torque, but also questions like this, just comparing rotational inertias. So on the equation sheet, you have this list. You don't have the pictures of them, but you have this list of rotational inertias. And so I might ask you which one is going to be easier to swing in a circle or spin or whatever else. And it's going to be the one with the least rotational inertia, the smallest amount. How you can tell from the equations is the number out front. Because if you have the same mass and the same radius or length, everything but the number out front is the same. And so the smallest one wins as far as easiest to spin. Calculation-wise for this chapter, I'd say the main focus would be questions like this one, where I give you some information. You have to find the net torque acting on your object, and you have to find its moment of inertia or rotational inertia, and use that to find the angular acceleration. So this is another one where if you have your list of variables, it becomes easier to tell you're dealing with this kind of problem. This is actually the same kind of problem. It's just if we're talking about equilibrium, the net torque is 0. And with these, I can kind of go a little bit crazier as far as what I can ask, because you at least don't have anything moving around. It's simpler conceptually, but that means more can be asked about the math. I would not go this crazy on an exam, but for instance, in the practice exam, there's ones like a guy and his son on a seesaw. And it's just a question of like either what is the son's mass, or if I gave you the mass, where should he stand on the seesaw in order for it to balance? Similar things like that. And for that, you really don't even have to look at the forces. You just have to look at the torques. He would produce a counterclockwise torque. The kid would produce a clockwise torque. And if you know how to calculate torque, it's force times distance times sine of the angle between them. then it's pretty easy to set up an equation saying how is the net torque equal to zero? How do you balance out these two torques? And that is, I believe, the main stuff for this chapter. Oh, and for angular momentum, I would expect more of a conceptual question than a calculation. So it would be something along the lines of this last one, but more asking about just the basic concept. For instance, if I have a setup where the rotational inertia of something decreases, what happens to its angular speed? The answer is it increases because it has to for angular momentum to stay the same, be conserved. If you lose a little bit of I, you got to gain a little bit of omega to make up for it and keep the product of the two the same. All right, I think that's the quickest recap I can do. So, any questions?
The two problems where you was like we're guaranteed to have two problems like that. On our TC, we can have those two problems under it. Or
Yeah,
is it
I'm
gonna be
not.
like,
So, when I say guaranteed, I mean a problem like this. It won't be this
yeah,
problem.
okay.
Yeah.
What
Say
is
again?
it? Like same format?
Yeah, I
So
mean,
like
a problem on kinematics for angular
okay,
variables.
That's what I was asking. I was thinking like were you saying like same formula, just different numbers or kinematics and the kinematics in general?
In general, so like
Yeah.
these were two different kinematic equations we had to use. It could be you have to use one of the other ones on the list, or it could be these again, but the setup or what you have to solve for is slightly different.
I did. I need to find the question number. Oh, number 37.
Okay. So is it a question about the solution, or do you want me to go through the whole thing again?
It was a question about the formula that was used to get it, and also like the the formula and like the switch of it, because like the formula. It's about
Okay, just where
yeah,
did this come from?
yes, where the formula comes from.
Okay, so it's asking for the center of gravity, and that's that thing where we called it a weighted average. It's saying if you've got weight distributed around a certain point, in this case, we could think of this as our axis, then how can we replace all of that weight with one equivalent weight? In other words, something that has the exact same weight as these four objects, but only sits at one location. What is that location? And that's what we call the center of gravity. So in the notes, that is um, in chapter 9, this equation right here. Does that answer the question?
It does, and then like the transition between the formula that we're looking at, and then for it to be like M1G plus M2, it just gets put not just put in there, but like the information that we're given with the question, the they switch out, if that makes sense.
Yeah, so we're given masses, and I know that because it's telling me stuff in kilograms, but center of gravity is about forces and in particular weights. So I need to rewrite that stuff in terms of the weight of each object instead of its mass. And weight is mass times g, mass times 9.8. So I'm just replacing it like we had to do a lot of the time in free body diagrams.
Okay.
Yep.
All right. I had another question.
Okay.
All right. So my next question is about kinematics. And like, is there a certain set of questions we should look at? Not questions, but like which kinematics we should look out more for than others, or like the well versedness in them all, if that makes sense.
Well, when I look at the kinematics problems, so in this thing, it would be, let's see, okay, 19, 21, 22, 23, 24 are all what I would consider kinematics problems. To me, they read the same in the sense that it's just giving me several different angular variables and then asking me for a fourth one. And so it's the same process. I don't really look at them as different questions just because I use a different equation, since every equation is on the list. Um, so I can't say that you can expect like this to show up more often than this equation or anything like that, because to me they're, any's just as good as the other.
Yeah. Okay.
Yep.
Is it is it gonna be a heavy? Is it gonna be a lot of heavy vocabulary questions on there, or like certain definitions? Need to know,
Um,
like by heart.
what would you
If that makes
consider a
sense.
vocabulary question from like a previous exam?
So the quiz that we like number 5 says as an object rotates, its angular speed
Oh, okay.
increases.
Um, I'd say you could maybe expect one like that. It would be one no work required question, and something along the lines of this object is moving in a certain way. What kinds of acceleration does it have? And it could be either centripetal acceleration or tangential acceleration or both or neither. Questions like that.
Okay. And I had another question, but it was a question from the quiz as well.
Okay.
So a bike wheel has an angular velocity of positive 5 radians per second and angular acceleration of negative 2.5 radians per second squared. And then which is true? The
Yep.
correct answer is the wheel will spin slower over time. But I ended up putting D because I thought because of the acceleration being negative.
So yeah, let's step back to for the angular velocity. You said it was positive, which means it's rotating counterclockwise, right?
The angular velocity was positive, yes.
Yeah, so counterclockwise. All right, for the angular acceleration, it's negative 2.5 radians per second, which means you could look at it as actually it's kind of this equation right here is one way to think of it. So this was the thing that was initially 5 radians per second.
Mm-hmm.
This is the one that's negative 2.5 radians per second each second. So after 1 second has passed, what will omega be? What will the final angular velocity be?
Oh, 2.5.
Yep. After one more second has passed, so 2 seconds overall, what will the final angular velocity be? 5 minus 2.5 times 2, that's 5 minus 5, or 0. We see that as time goes on, this starts at 5. After 1 second, it's 2.5. After 2 seconds, it's 0. So what's happening to that angular velocity? It's decreasing, right? It's slowing down. So you can sum that up by saying if I start with a positive angular velocity but have a negative angular acceleration, the object will spin slower over time. The most general rule is if they have opposite signs, slower. If they have the same signs, faster. Malak, did you have any questions?
No, sir. Thank you.
Okay. Jakayla, did you have any others?
I did not.
Okay. Well, if that is it, then we'll call it a day.